Yeah, this is a simple pendulum. When you leave it like that, it is going to settle at an equilibrium position. It's not going to move after some time. When you displace it slightly like this, it is going to move to and fro like this. So in this case, we say it is oscillating. So it is a kind of motion we refer to as simple harmonic, a motion that is repetitive. So this kind of system is referred to as a simple pendulum. So this line where the pendulum settles is what we call the equilibrium position. This is the equilibrium position. This is our pendulum, which represents this. So it looks like this. So that line there where it settles is what we call the equilibrium position. So you realize that when we were oscillating it, we had actually displaced it through a certain angle. So what you see there, that theta there, is the angle of displacement from the equilibrium position. So you displace it like this to that, and you see the pendulum has a weight itself. The weight is the mass multiplied by the acceleration due to gravity. But this weight can be resolved, and we have the vertical component of the weight, which is responsible for restoring the pendulum to its equilibrium position. Yeah, so that component of the weight which restores the pendulum to equilibrium is given by mg sine theta. This one you should have learned it in Form 3 about resolution of forces. Yeah, so that is the component responsible for restoring. It is mg sine of theta. The displacement is x, which was in the opposite direction. You realize that the restoring force is taking the pendulum to the opposite side, to the direction of the displacement here. So we know from Newton's second law of motion that force is directly proportional to the rate of change of momentum, and when we narrow it down, we would end up with the force equals to mass times the acceleration of the body. Yeah. So in this case, we are going to replace our force, which is ma, which is given by ma, by that restoring force, which is mg sine of theta, because that one is a force. Yeah, but we introduce a negative sign there. That negative tells us that the restoring force is acting in the opposite direction to that of the displacement. That's why you see a negative there. Yeah,